And we'll get back to this. And let's take a look here. So we started talking a little bit about this. So one thing we went over was the basics of just simply using a ruler. And so, and somebody texted me a great question, right? So when you put an object down there, you look for the mark. So in the case of ruler A, the first one was the 4, right? So the general rule is you when you use a ruler, you when you put the object and you try to line it up. Most of the time, we line up with 0. So for this ruler, that's 4. And then we have to, since there's no other marks, we have to estimate. And of course, we by eye can sort of break it up. And yeah, and we went through a whole discussion of this. Let's go back because it's already in our notes. And or is it here? Yeah. So we pick we get that number, and then we have to estimate the next number, and then we went through a discussion here, and then right here we noticed, oh well, we can get a better number. Okay. And then I believe we talked a little bit about this, but I'm just going to reiterate. So there's other things now. There's technique, and I think I showed this to you. I just don't see it written down in my notebook here. So either it's I didn't do it, or I was so busy that I didn't write it down. Yeah, I'm getting it. It's coming back to me now. Now, my wood block that I actually used is a little bad for this because it's a children's toy. I got a huge amount of these made. They're beautiful maple blocks. It has this chamfered edge, those to be a little safer. So I'm going to use this wood block because it has nice even edges. And this is when I was hoping we would be talking about the density. So I got 3 different wood blocks, but since we're falling behind a bit, which is my fault, but what can you do? So the idea was that when you take a measurement, there can be a certain amount of error in. So when I look at this, to me, and now to you guys, the way it looks, it's exactly at 15. But if I were to go like this, and in fact, let's see, I need to, let's make this bigger still. Oh yeah, so you can see it now. It's not quite, if from your point of view, it looks like it's more like 14 point, it looks like it's more like 14.9. But when you look straight down at it, and the idea is what you do is you try to make sure that, like if I go here, see, I can see the end of the block. And so as I bring it up and I go, now, of course, if I go too far, there's no way of knowing anymore, right? So it's a bit of a trick to go just far enough and then start going back, and just till the edge, the side of the block disappears, then I know I'm looking straight down on it. And that's called parallax. And, it's a big fancy word, and you can sound real smart saying it, like supercalifragilistic, if you've ever seen Mary Poppins. It's summing up this word, and you've got a lot to say. So that's called parallax. So we talked about taking readings with the ruler. And one of the things, and there's other ways, there's other things you could think of about how you might make the measurement better. So let's see, 2, 17, 21. Yeah, I have to get this. How can we make this better? Yeah, if I make it bigger, I can't write small enough to fit it where it belongs. And the time 11:33, and my initials. So parallax, and then we finally figured out how to use the ruler here, but I am going to cheat, and I'm just going to make a box. If I was doing this, I would use my ruler and draw it out on the lines, right? Of the spreadsheet. Oh, I want spreadsheet. Forgive me. The my logbook. And let's make the outline a little heavier, just to. There we go. So now, if I had me a ruler up there, and somehow this feels familiar. I did this somewhere, maybe not with you guys. And so when I want to take my measurement, I want to make sure that, oops, my eye is directly above. And we don't want it to be here. This is the good eye. And this is the bad eye. And if we look down perpendicular to the block edge, we minimize error. And if you were to be writing up a formal report about some measurement, this is the kind of thing you have to describe to people. When we took this data, which I think you probably want to write down in your logbook, when to minimize error, we made sure to look straight down. And this error here that's introduced, again, this is called parallax error. So we try to use rulers that have more, okay, slow down, to minimize error, blah, 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 blah. Okay, so we talked a little bit here about the ruler itself. So equipment, we can use a better ruler. So to get better measurements, and this is kind of, I guess, a summary that we could talk about later, but it also helps us as an advanced organizer, better measurements. We use more precise ruler, right? We saw that when we used the ruler with the millimeter marks, we could get more decimal places, or use more precise ruler. And then, and so this is basically on the heading of instruments or equipment. And this is why it's important to describe your equipment. And then technique. And so in both cases, it's important to write down how you took the measurement. So we took a ruler, we dropped it onto a block randomly, we made sure to, and we measured that we took our overhead straight down view to reduce parallax error. And parallax error is the apparent, you get a number that's the correct number, but if you don't look straight down, if you look at an angle, you have a possibility of a false reading, and it has to do with the thickness of the ruler. If you think about it, another way to minimize it, of course, would be to use a clear ruler. And one of an advantage of a clear ruler is that, and this really hopefully will dramatically show us the parallax error. Let's see if I can do that. So I will claim that I have it directly on the 12, right? But if I go way over here, yeah, it's obviously not on 12 anymore. It's very, I don't have, I don't know if I can focus that. Oh, that's a little better. Yeah. And if I bring it over here, yeah, now it starts looking like it's more than 12. It's kind of hard to see. But you can just take your own ruler and convince yourself. There you go. And so and another cool thing about the clear ruler is that in this case, I'm trying to, this is nice because this ruler has the markings on the bottom. Wow, so that's really nice. So that makes it much better, right? So I can even accentuate the parallax error by putting it with the markings on top. Oh, cool. Get together like this, even though I've been a little scatterbrained on you guys. Oh, this is cool. Now you see the two, and of course I have to stay on the screen somehow. There we go. And oops, I moved a little bit. Well, it's a 3, not a 2. And then if I'm like this, glare, where is the glare coming from?
Professor, we can't hear anything. It's lagging.
Yes. You just can't focus it. Oh man. Hey. How's that? Yep. All right. So you should be able to hear me now. Yes. The video. Okay, I gotta slow down. Yeah, I bought this Bluetooth headset here, and it's supposed to go 20 hours of talk time. I gotta return it. Okay. All right. Oh yeah. So again, this camera is not doing the job, but still. But I didn't realize that this thing has the marks on the bottom, which is very nice. That because the parallax error in this case comes from the thickness of the ruler, and this is for a piece of crap ruler. That's pretty cool. Okay, so we went over, yeah, a little bit of this. So let's motivate this, what's going on here. And so, excuse me. So let's, oops. And this one has last time, so I will make a new slide. And so we have 2, 17, 21, and it's 11:42, date, time, initials. Okay, so let's say we have two numbers, right? So first of all, we have for the length measurement. So here's an example error calculation. So we determined the length by having an L1 and an L2, and they each had a plus minus. So we want to say, all right, if we say L itself is equal to L2 minus L1, great. And so let me take one of my numbers from my spreadsheet, if I can find it easily. Oh, that's the ticker tape. So I have 17.2 and 3.4. So I have L1 equal to 3.40 centimeters, and L2 is equal to 17.20 centimeters. Now you notice I quoted a larger error than what we were quoting. So I'm saying both times plus minus 0.2, and we determined it to be 0.02. But because I didn't give you guys the best ruler. If you looked at, 0.2. If you look at I have to do single line cross out, plus minus 0.2 cm. And if I'd have provided you with the proper ruler, if we were in class, whatever. So now we plug in 17.20 centimeters minus 3.40 centimeters, and we get let's see, that's 8. Oh, cross out. 0 from, I could have kept that. 0 from 0 is 0. 4 from 12 is 8. 3 from 16 is 13. 3 from, is that what my spreadsheet says? Let's see if I can check my math, 13.8. Oh, I got it right. Okay, so how do you assign a plus minus to it? Well, there's a couple things we could do. We could say that we said plus or minus 0.2, right? So let's make this 17.4 minus 3.2, and we can say, all right, now it's 0.20. 3 from 17 is 14. Or we could go the other way and say 17.00 minus 3.6, which is going to be 0.4 and 13.40. So then we say, okay, the final answer is 13.80 plus or minus, let's see, 0.4, 0.4 centimeters. Now, in this case, it's not real dramatic, but we should think about this and say to ourselves, I don't really think that whenever I take a measurement, I don't really think that I'm always this far off. I think that most of the time I'm going to get a pretty good, I'm going to get the real number. Excuse me. And so we have this table And I decided we'll just focus on the formulas that we need. And I'm just looking for it. Let me copy it, huh? Control C, error propagation short form. And these formulas here, and I talked about it a little bit last time, I think. And I use this table when I write a paper. And so we're going to use this one here for this. This is for addition. So F equal, whatever you're determining equals something like this. And it could be minus as well. It doesn't matter. A, little a times capital A. And I'll explain the terms in a minute. And it's either plus or minus little b times capital B. And the sigma here, the definition of the sigma here is our plus minus. We went over this last time. And then a little a and b are constants, just in case, like if you did 2 pi plus something, constants. Now, sigma, this is, for us, is always going to equal 0. And it just means that if there's some kind of relationship between the two measurements, but we know that the two measurements don't have anything to do with each other, so we don't need the sigma AB. So at the end of the day, and for the most part for us, little a and b are going to be 1. If there's ever a chance it's not, we'll go back over it. So what this becomes then is, let me think it through. Oh.
Do you mind zooming in a little bit for the formula, please?
So we're going to say, for our case, we have L. Oh, of course, I'm sorry. I can't. How's that? Oops, why did that happen?
Okay. I think it froze.
I lost the logical thread here. Right. So what? You can't, what, can you see what I'm working? It's got some lag going on.
It's good.
Can you see it now?
Yeah, it's perfect.
Oh, okay,
thank you.
Great. All right, so hold on. Oh, okay, great. So when we say that the two things are independent, I finally thought of a good way to think about it. If we think of a right triangle, right? And we think of this as sigma capital A and sigma capital B, then we're going to say that the sigma on F is the hypotenuse. Because remember, we said the two of them are not dependent on each other. And in math terms, that means that the measurements are orthogonal. And in XY, that means they're at 90 degrees to each other. So we know the Pythagorean theorem says that sigma F squared is going to equal sigma A squared. And then we just simply take the square root of it, and you see how we end up with something that's not quite the worst case scenario and not quite the best case scenario. So let's, and then the final answer is sigma F equals sigma A squared plus sigma B squared to the 1/2 power. So now what we do is we plug in our axial numbers. So it's sigma L equals sigma L1 squared plus sigma L2 squared. And we do the 1/2 power again. So that was 0.2 squared plus 0.2 squared square root. So that's 4 plus 4 is no, 0.04 plus 0.04. And so it becomes 0.08, square root of 0.08. And so then we just take our calculators. .08 square root, and it becomes 0.28. So you see how now we would expect it to be a little bit bigger, but than 0.2, but we really wouldn't expect it to be as big as 0.4. So at the end of the day, then we have L and sigma, remember, is plus minus L equals to, what do we get? Cm plus minus 0.28 cm. Okay. Do you see my mouse screen, my mouse moving around? No, Tamara?
It like takes a while to catch up. Maybe like 7
Let's
seconds.
try.
Yeah, I think
Stop.
even when you hear us lagging or
Okay.
like, there's, I think that moment.
Wow. Wow. Okay. Okay. So, well, luckily that's what's nice about having it written down here. Yeah. Okay. So the motivation here is that we need to add the errors some way that kind of reflects the fact that we're not going to, every single time we take a measurement, do the worst possible measurement. We expect that our measurement, for the most part, is going to be good. And that's what doing the Pythagorean theorem thing does to help us. Excuse me. Okay. Can I make a new page? Can I go to a new page? I'll just, well, you know what? I'll wait for somebody to yell at me to go back. New slide. Oops. Yep, of course.
Oh, okay. You got it.
And I need to scroll it down, I think. Yep. That's the bottom. Now, remember, you guys should add some descriptive words in here, okay? Because I didn't add any notes. Yeah. Okay, so here's what it's on. It's on Canvas. And you go to oops, Scroll up. Excuse me. So go to short form because you'll just lose your mind if you look at this one. The math is really heavy. Propagation of uncertainty. And so for physics 1570, we use, right, so there's the minus, but they're basically the same formula. We use, these are for adding and subtracting things, and then we use for multiplying and dividing, but notice each time they're the same formula. Okay. And they're also in the spreadsheet too. So one last thing we need before we move to the spreadsheet is recall that we talked the volume, the plus minus on the volume. So I just wanted to reiterate that in terms of my inspiration to use the Pythagorean theorem idea. Okay, so we have 2, 17, 21, it's 11, 59, and there's the date. Okay, so we have update on the plus minus volume determination. Deter, yeah, I can, in nation. Imagine I learned how to where to put a hyphen when I was in grade school because we didn't have, even when you have a typewriter, you have to figure it out, right? Word processors were on the distant horizon. Okay, so, excuse me. We have L plus minus L, whoops, plus minus L, W plus minus W, and H plus minus H. And this is, we've already seen this, L times W times H. And once again, if you were to do you could figure it out and you'll see a huge swing. So give me a minute, let me think about this. Right, we could do plus volume equals to L plus minus L times W plus minus W times H plus minus H. And we could do a negative all. You'll know if you do it, at least do one of them, you'll see it makes a huge number. And again, we just don't believe that we're that inaccurate all the time. So you remember from last time, the way to understand this is to remember the definition of fractional error. Fractional error. And fractional error is the plus minus of a value divided by the value. And we sometimes use the symbol, this lowercase delta. And why would you do that? And why do you not do it when you do the plus minuses? Excuse me. In the plus minuses, when you add and subtract numbers, first of all, the sig figs comes from the number of decimal places, but for us, it's always going to be the same. But let me think about this for a minute. Why do we use we don't use the fractional error for plus minuses? I have to think on that one. I know why we use it for the multiplication process, because what happens is if I measure, so for example, if I measure 50 centimeters plus minus 1 centimeter, we would think that this is pretty good. If we were to measure 5 centimeters plus or minus 1 centimeter, we'd say, well, yeah, meh, it's not that great, huh? But if we now want to sort of use our Pythagorean theorem idea, we are not going, our answer is not going to reflect the fact that this is very good and this is so-so. So if we look at the fractional error, 1 over 50 or 1 over 5, now we can obviously see that this is a much better measurement. And if we did it earlier, what if I got to think about that one. That's a good point. I need to motivate that one. So now in the case of length times width times height, remember we had that it's not exactly Pythagorean theorem anymore, because we have 3 variables, and it's, so this is of f, and you can go back in your notes to look at it. So what we do now to get the we get the fractional error of v, and that equals the fractional error of L squared plus the fractional error of, W squared plus the fractional error of H squared. And this makes sure that each one of the errors, depending on, again, this weights them properly. This way we know this is a great measurement, but this one here is not so good. So it's going to contribute more error to the final answer, and it should. Now, the only thing now we have to remember is that we don't want fractional v, we want plus minus v. So we just had to remember that this delta v also equals plus minus v, so let's box this, over v. So what this implies is that plus minus v equals to capital V times the fractional v. So now, yeah, I'm hoping this gives you a better feel for what's going on here. Whenever you have things that you measure, that one measurement has no effect on the other measurement, we do this kind of Pythagorean theorem thing. For the for adding and subtracting, we simply use the plus minuses or the sigmas. And for multiplication and dividing, we use the little delta, the fractional error. And that's why it's in the table. So for addition, subtraction errors, and this is called error propagation. For addition, subtraction, error propagation, we use the plus minuses or the sigmas. For multiplication, division, error propagation, we use the fractional errors, which is the plus minus value divided by the value. So let's put plus minus value. And this is how when you tell people you made some measurement, and like you say, you measured the volume of the block, you can tell them how good of a job you did. All right, so I'm going to switch the spreadsheet, so you're going to yell at me to go back to